The materials required for this experiment are 1 mole per liter sulfuric acid, potassium permanganate of unknown concentration, a small beaker, a 100 milliliter graduated cylinder, some distilled water, iron 2 ammonium sulfate hexahydrate, an Erlenmeyer flask, a 100 milliliter volumetric flask, a pipette bulb, a funnel, a plastic tray, a scoopula, safety goggles, a retort stand, an electronic balance, a 50 milliliter burette with stopcock, a pipette, an eyedropper, a stirring rod, and a burette clamp. Always wear goggles and an apron to ensure that hazardous substances do not come into contact with your eyes or skin while performing the titration. A titration is where a solution of unknown concentration is reacted with a solution of known concentration in order to determine the concentration and other properties of the unknown solution. In a redox titration, one of the solutions used is an oxidizing agent and the other is a reducing agent. The equivalence point is reached when the correct stoichiometric amount of oxidizing agent has reacted with all of the reducing agent. An indicator in a redox titration changes color between the reduced and oxidized states. The endpoint occurs at the moment the indicator changes color, which is where you end the titration. The titrant is a solution of known concentration which is added to a second solution to determine its concentration. In this titration, the iron 2 ammonium sulfate hexahydrate solution is the titrant. The analyte is a substance of unknown concentration in its titration. In this case, the potassium permanganate solution is the analyte. The analyte potassium permanganate is self-indicating. The permanganate ion is a strong purple color. It is also a strong oxidizing agent, especially in acidic solution. In this titration, the permanganate ion acts as the oxidizing agent and will be reduced to form the manganese 2 ion. Iron 2 will oxidize to form iron 3. When the titration is past the equivalence point, the permanganate ion will be present in excess, and the resulting solution will have a permanent color, indicating the endpoint. This lab requires us to prepare a 100 milliliter, 0.05 mole per liter solution of iron 2 ammonium sulfate hexahydrate. If we multiply the concentration of 0.05 mole per liter and the volume of 0.1 liter, we get that 0.005 moles of iron 2 ammonium sulfate is present in solution. In order to convert that to mass, we multiply the number of moles by the molar mass of iron 2 ammonium sulfate hexahydrate, which is 392.21 grams per mole. By doing that, we get that 1.96 grams of iron 2 ammonium sulfate hexahydrate are required to prepare 100 milliliters of 0.05 mole per liter solution. First, we must measure out the appropriate amount of iron 2 ammonium sulfate hexahydrate. Begin by placing the plastic tray on the electronic balance. Then, re-zero the balance. Using the scoopula, measure out 1.96 grams of solid iron 2 ammonium sulfate hexahydrate. Using a graduated cylinder, measure out 50 milliliters of distilled water. In order to measure liquids, a graduated cylinder must be used. Equipment such as beakers or Erlenmeyer flasks should not be used as they aren't calibrated well enough to give an accurate measurement. Always use the smallest possible graduated cylinder so you can get closest to the exact measurement. Measurements made by using a graduated cylinder are usually taken to the tenths place. The last digit in the tenths place is uncertain. For example, if you have a measurement of 10.5 milliliters, the 1 and the 0 are certain, while the 0.5 is uncertain and estimated. Always measure from the bottom of the meniscus. This graduated cylinder goes up by increments of 1, with the shorter lines representing increments of 0.1. We know for certain the measurement is between 8 and 9 milliliters. Measuring from the bottom of the meniscus, we can estimate the measurement to be 8.6 milliliters. Always keep your eye in line with the bottom of the meniscus when taking the reading, otherwise the resulting reading will either be too high or too low. Transfer the iron to ammonium sulfate hexahydrate into a beaker, followed by the distilled water. Using the stirring rod, stir the solution thoroughly. Next, using the funnel, transfer the solution into the volumetric flask. Rinse out the beaker into the volumetric flask to ensure there is no solution left inside the beaker. Fill the volumetric flask up to the 100 milliliter mark with distilled water. Remember that the bottom of the meniscus should touch the 100 milliliter mark on the volumetric flask. Stopper the volumetric flask, then invert it a number of times to mix and prepare the standard solution. Run some distilled water through the burette in order to avoid contaminating the potassium permanganate solution. Open up the stopcock and collect the wastewater in a container. Also, clean the pipette with distilled water. Measure out around 60 milliliters of potassium permanganate solution using the graduated cylinder. Dilution of the potassium permanganate solution can be a source of experimental error, so run some potassium permanganate through the burette to prevent the dilution of the solution to be used in the titration. Once again, collect the base potassium permanganate solution in a container. Ensure that the stopcock is closed, then fill the burette to around the 0 milliliter mark with potassium permanganate solution. Another source of experimental error can be air bubbles in the middle or tip of the burette, which will result in an inaccurate burette reading. In order to get the bubbles out, open the stopcock and drain some liquid out of the burette. If there are bubbles in the burette above the tip, gently tap the side of the burette and the gas bubbles will rise to the top and out of the burette. Unlike a graduated cylinder, burettes are read by looking at the empty area in the burette above the liquid. The 0 ml mark is at the top of the burette instead of at the bottom. Once again, keep your eye level with the meniscus when taking the reading. For instance, the reading on this burette is 21.3 milliliters. In order to calculate the volume of liquid dispensed from the burette, subtract the initial volume from the final volume. For example, if the final volume is 20 milliliters and the initial volume is 5 milliliters, the volume dispensed is 15 milliliters. Pipette 10 milliliters of iron 2 ammonium sulfate hexahydrate solution from the volumetric flask. Remove the pipette bulb and use your index finger to seal and release the top of the pipette to remove any excess solution. Sealing the top of the pipette with your index finger, transfer the 10 milliliters of solution into the Erlenmeyer flask. Using the eyedropper, add 10 drops of sulfuric acid into the Erlenmeyer flask. Place the Erlenmeyer flask under the burette and open up the stopcock to begin the titration. Slow down the flow of the potassium permanganate solution when the purple color begins to linger longer in solution. Keep shaking the Erlenmeyer flask throughout the titration. Note that the indicator does not change color at exactly the equivalence point. The darker the indicator color gets, the further the titration is past the equivalence point. Overshooting the endpoint can be a source of experimental error, as it will give a greater volume than necessary of potassium permanganate solution to react completely with iron 2 ammonium sulfate hexahydrate solution. This in turn will give an inaccurate calculation of the concentration of the analyte. Therefore, ensure that you end the titration at the point a permanent pale yellow color occurs. Conduct 2 more titrations, each with 10 ml samples of the iron 2 ammonium sulfate hexahydrate solution to verify the accuracy of the results. Note that it is unnecessary to refill the burette up to the 0 ml mark. Simply subtract the initial burette reading from the final to get the volume of potassium permanganate solution dispensed. Clean all items used in the lab with distilled water. In order to clean the pipette, use the pipette bulb to fill it with distilled water and then empty into the waste container. Ensure that any spills are cleaned and that all waste liquids are emptied into the designated container. Do not empty waste chemicals down the drain to avoid releasing harmful chemicals into the environment. Calculate the average volume of potassium permanganate solution dispensed by adding the results for all 3 of your titrations and then dividing by 3. The average volume for this titration is 9.9 milliliters of potassium permanganate solution. In order to calculate the concentration of the analyte, first calculate the moles of iron 2 ammonium sulfate hexahydrate in solution. Multiply the concentration at 0.05 moles per liter by the volume of iron 2 ammonium sulfate hexahydrate solution in the Erlenmeyer flask. Since the permanganate ion and the iron 2 ion react in a 1:5 ratio, divide the number of moles of iron 2 ammonium sulfate hexahydrate by 5 to give the number of moles of potassium permanganate that participate in the reaction. We get that 0.0001 moles of potassium permanganate participate in the reaction. Divide the moles of potassium permanganate by the average volume of potassium permanganate solution dispensed during the titration. By doing this, we find that the concentration of the potassium permanganate solution is 0.01 moles per liter.